Okay, so we got some 8.1 questions, and then we're going to do that dreaded solubility quiz question again. Let's start with 8.1, number 15.
Okay. It's asking for the voltage of the cell at 298 Kelvin.
Okay. Whoa, I need more information than that.
Yeah, it has the cell thing.
Yeah, the
What is it?
Yeah.
Cu copper solid.
Well, you might have different ones. Do you have the same one?
No, it's slightly different.
Let's get yours since you were the one asking.
Okay. Copper solid, and then the next part of the cell is copper 2 plus at 0.51 molarity. And then, yeah, the two lines, Ag plus at 2.83 times 10 to the negative third molarity. And then just Ag solid.
Okay. How do we even begin a question like this? Well, we don't have to write, I mean, we are going to need a balanced equation, but the first thing we have to realize is that we're dealing with a non-standard cell potential. Since we're dealing with a non-standard cell potential, we'll be doing the Nernst equation, or the non-standard cell potential equation. Hang on, my pen just ran out of ink, too. So I always like to start with that kind of thinking. You know, there's a lot of information here. We are going to need the balanced chemical equation as well. But we can start with recognizing that E cell is equal to E cell naught minus RT over NF ln Q. And as soon as I write that down, I'm like, oh, I need the balanced chemical equation so I can figure out what Q is. That's going to be copper plus 2 Ag plus goes to Cu2 plus 2 Ag. Got to get our states of matter in there so we know we are allowed to disregard in the Q value in which we have to include. My Q is going to be products over reactants. It's going to be the copper concentration divided by the silver concentration. This is the part most people forget. Squared. Right, I can also tell that this is going to have an N value of 2. There's going to be 2 electrons transferring. I can also calculate the standard cell potential for this. I can calculate E cell standard by doing silver to copper. That's going to be 0.8 minus 0.34. That's going to be 0.46 volts. I'm going to grab a calculator and double check that. Oh, that's not how to check. 0.8 minus 0.34, 0.46 volts. Okay, now I can start plugging things in to my non-standard Nernst equation, or my non-standard cell potential equation. And I can say my E cell is equal to 0.46 minus 8.314 times 298 divided by 2 times 96485. Natural log, products over reactants, is going to be copper concentration over silver concentration. 0.51 divided by 2.83 times 10 to the minus 3 quantity squared.
So it's not 2 to that squared because it's not the stoichiometric.
Correct. Right? It's not saying how we got to that concentration. How we get to that concentration would have some factor of 2 in it. But it's saying it is that concentration already. So we don't need to double that. We just need to square it.
Okay.
Were you doubling it?
Probably, yeah.
Okay. So yeah, that whole point of when we know that this 2 in the balanced reaction comes in place in two different ways. It comes into play stoichiometrically, and it comes into play energetically. That's to say in the Q's and the K's. Stoichiometrically, we're not doing any stoichiometry here, so we don't need to do any of the times 2, the times 2's. But we are using it in this Q expression, so we do need to do the squared.
Okay.
So let's go ahead and finish it out. 2.83 times 10. Oh, my calculator's off. 2.83 times 10 to the minus 3 squared time, inverse times 0.51. Oh, I messed up. 2.83 times 10 to the minus 3 squared inverse times 0.51. Wow, that's a huge number. Natural log times 8.314 times 298 divided by 2 divided by 96485. Okay, we eventually get down to something reasonable. Okay, and then we're going to do plus 0.46. So I get a cell potential, non-standard cell potential, of 0.318 volts. Assuming I didn't make any typos. I was really worried that I did something wrong because while I was doing all the math, before I divided by 96485, I had something that was like thousands. But I guess that makes sense because I'm dividing by 96,000.
So when it comes to that term in the middle there too, is it like, yeah, or just that entire fraction part? Is that in terms of joules?
Let's double check all the units. I believe it ends up in terms of joules and volts.
Okay.
Right, because the 8.314, so if we do our unit analysis here, I'll switch colors for that. Let's go to green. Where did I get the green pen go? Oh, there. Nope. Oh, well. Oh, yeah, that one. Thank you. The one I keep throwing. So, the 2 here is moles of electrons per mole of reaction. 96485 is coulombs per mole of electrons. So that will cancel out coulombs, and we'll essentially just end up with something that is in coulombs per mole of reaction. The 298 is Kelvin. 8.314 is joules per mole reaction. Kelvin. Gotta double check and make sure I didn't forget anything on that. Joules per Kelvin mole. Well, that's it, right? And in most of this stuff, it just says moles, 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 but I like to specify moles of reaction. So moles of reaction cancels, moles of electrons cancels, coulombs cancels, and you're just left with joules. So this entire thing ends up in units of joules per coulomb, which is volts.
Okay.
Which it better because our standard cell potential is also in volts.
Right. Okay, thank you.
Okay. Should we look at number 19?
I think I should be able to figure out 19. It's
19 is
sort of
pretty much
question,
the same
yeah.
thing. What about 20?
That one is still good. It's oxidation number for.
Oh, yeah. Okay, so let's look at number 20 together.
Yeah.
This is something that I thought a lot of you got in 124, but maybe not. So this is how we determine oxidation states of organic compounds. Which molecule is this one?
I can just show you the picture.
Yeah, show me the picture. Okay, so let me redraw that on the board real quick.
Which number is this? Which question?
20.
Number 20. Is it 20?
Yeah, 20.
Right. And then we got a nitrogen there. We got a nice little ring structure. I drew my ring a little lopsided, but, you know, got an oxygen there. Got a fluorine there.
And I think that's it.
That's it? Okay. And then we just label all of these things as 1, 2, 3, 4, 5, 6, 7, 8, 9. And we say, what's the oxidation state of the different compounds in an organic compound? I'm going to do, so you can go ahead and sit down. And we'll just kind of like, you'll have to tell me which carbon is which.
Sure,
So to think about this, I'm going to do a little side problem that's easier, this one first. Again, that I thought a lot of you got in Chem 124. So It's okay if you didn't. But essentially we're going to assign oxidation states. Assign oxidation states for ethanol. I draw the Lewis structure explicitly. Right, and the trick here is, let's see if I can remember the phrase I used yesterday that I liked. Right, so what we have to do is we need to count electrons around each thing with electronegativity in mind. So the way I kind of go about this is I first say, look, each bond is 2 electrons. So I'm just going to turn each bond into 2 electrons. Okay, and now what I have to do is for each thing, I have to look at it and say, okay, here's oxygen. Oh, oxygen has lone pairs on it as well. That's important. Right? Oxygen is more electronegative than carbon, and it's more electronegative than hydrogen. So when I consider its electrons, I will consider all of the electrons around it as belonging to it, because it's more electronegative. In this situation, my hydrogen started with 1 electron, ended up with 0 electrons. That's going to equal +1. Hydrogen ends up with a +1 oxidation state. Oxygen, in this case, started with 6 electrons, 6 valence electrons. Right? This is we were supposed to do this when we were doing like valence electron configurations and Lewis structures. So it starts with 6 valence electrons. It's kind of like formal charge, but with electronegativity in mind. Started with 6 valence electrons, ends up with 2, 4, 6, 8 electrons. I'm going to subtract the 8 that it ended up with because the electrons are negative. And that's going to get us an overall -2. So this is going to end up with an oxidation state of -2. Makes sense. Hydrogen's usually +1, oxygen's usually -2. The reason we see that is because hydrogen is usually the least electronegative thing in an organic compound, and oxygen is usually the most electronegative thing in an organic compound. The place where it gets a little bit weird is when we start looking at the carbons. Now, carbon is slightly more electronegative than hydrogen, so it's going to get both of those electrons and both of those electrons. But carbon to carbon, same electronegativity, they're going to split those. Same thing happens over here. Right? And so now I say, okay, this carbon in the middle started with 4 electrons, 4 valence electrons, 2, 4, ends up with 5 electrons. That carbon has an oxidation state, whoa, that's bad math, has an oxidation state of -1. That one got sloppy. Because it ended up with more electrons than it started with. In this kind of theoretical mapping of how electrons are unevenly getting shared, which is kind of like getting at the idea of oxidation state. This carbon started with 4, ended up with 2, 4, 6, 7. That carbon has an oxidation state of -3. Now the reason this is important is because it turns out that carbons can have different oxidation states in the same molecule, right? Depending on what they're attached to. Being attached to something that's very electronegative gives it a different oxidation state. Being attached to things where it's the most electronegative, hydrogens and other carbons, gives it a different oxidation state. So we get this difference in oxidation state depending on which carbon we're looking at in the molecule. You'll often also just go for the average. So ethanol is C2H6O. And you can just calculate the average. This is hopefully what most of you did, right? Hydrogen is going to be like a +1, oxygen is going to be -2. So I'm going to end up with 2x plus 6 minus 2 equals 0. X is equal to -2. Right? So this is just saying I have 2 carbons with unknown oxidation state. 6 hydrogens, each with a +1, 1 oxygen with a -2. The average that's the average carbon oxidation state is -2. So -3 and a -1, the average is -2.
Well, since there's 2 carbons, wouldn't it be -1?
No, X is the average because it's taking into account that there's 2 carbons. So each carbon needs to be -2. Right? But they don't both have to be -2 because they're not attached to the same things. So we end up with 1 carbon -3 and 1 carbon -1. And this is the process for figuring out the oxidation state of organic compounds, or carbons in inside of organic compounds. Inside of organic compounds, oxygens are almost always -2, hydrogens are almost always +1s. I don't think you really get things less electronegative than hydrogen inside of organic compounds unless you're doing really weird chemistry. So with this in mind, let's go ahead and look at this molecule and pick at least one of the carbons to try. So tell me which one you want me to do. Tell me when to stop. Which one is it? Well, just tell me. Which one was it?
Okay.
How about the one right to the nitrogen?
Yeah, that works.
This one?
The one to the right of the nitrogen.
Which one?
To the right.
There's 2 to the right. There's this one and this one.
First one.
The first one.
This one?
Yes.
Okay. Let's go ahead and look at that carbon.
I'm seeing as like the nitrogen's like the fork in the road. If you turn right, then you get like.
Bottom right or top right?
I know, but like if you look at it like that. With
Oh, you're
nitrogen being the
turning
fork-
right. Okay,
Yeah.
yeah. Okay,
Like,
I look at it in a different way than that. Okay, so we're going, because I look at it as a split, and you can split to the top or the bottom. But in any case, we're going to look at this carbon. Right, so to look at this carbon, what I'm going to do is I'm just going to draw the structure around that carbon. So I'm going to have a carbon, double bonded to a carbon, single bonded to a nitrogen, bonded to a hydrogen. And now I can figure out the oxidation state around this thing. And I do the same thing that I did before. Right? The carbons are going to share those electrons, so that gets split. It's going to take all of those, but it's going to lose it to the nitrogen because nitrogen is more electronegative. So this is going to be 4 minus 4. It should have an oxidation state of 0. Should we do another one?
Sure. How about the one to the right of, yeah, that one.
Okay. Okay, so if we're looking at this carbon, I can already tell it's going to have a different oxidation state because it's attached to fluorine. Fluorine is pretty electronegative, so I think it's going to have a different. Okay, so I'm going to take this, I'm going to do carbon to fluorine to nitrogen to carbon. And same thing again. And I say, okay, taking electronegativity in mind, carbon is pretty much, fluorine is going to take both of those. Carbon's going to share 2 electrons with that other carbon. Nitrogen's going to take both of those. We're going to end up with a situation where carbon starts with 4, ends up with 2. That's going to be a +2 oxidation state. Makes sense because it's got fluorine and nitrogen both attached. Those are both more electronegative than it. So they both kind of change that oxidation state, increasing that oxidation state of carbon.
By getting rid of those 2 electrons?
Effectively, right? Now, it's not like fluorine is ionizing the carbon to create like a cation, but it's creating this charge-like state of the carbon, which is the oxidation state. And I put big quotes around charge-like. Right? And this is again one of those like important definitions in the difference between charge and oxidation state that I brought up when we first got into redox reactions again. Is a lot of the times in 124, except for like these organic compounds, charge and oxidation state were interchangeable. Aluminum +3, the charge is +3, the oxidation state is +3. Iron +2, the charge is +2, the oxidation state is +2. Right? That's because we're actually making ions, and so they have those charges. But when we're looking at covalent compounds, this thing is overall neutral. There is no charge on this thing. But we can look at the oxidative states of the different elements inside of the compound to talk about how the electrons around it are behaving, which might give us insight into where different reactive sites are in the molecule. Sites of high electronegativity are usually high reactive sites. That was number 20. Good question. I had some people ask yesterday, but I wasn't recording, so I'm glad I recorded that. Okay, so that takes care of 15, 19, and 20. Did you have any specific questions?
More about the lab.
Yeah, we can do lab questions too. That's totally fine. I do want to talk about the solubility one on the quiz, and then we can also talk about the lab. Other specific questions? Anything else from 8.1?
I was going to ask about the corrosion lab.
Let's do some corrosion. Let me do this solubility quiz question, and then we'll do the corrosion lab if we're done with 8.1.
Mine is also a question about like the oxidation states, but for like the corrosion lab, like that question about like what's the oxidation state of the carbons and stuff like that. Like just like this, but just, like,
Same thing. Just got to identify the Lewis structure around the carbon it's asking about and go through the same process.
Wait, I have a question about the oxygen. Why does it start off with 6?
So we're looking at the valence electrons that it has. So if we look at oxygen on the periodic table, 1, 2, 3, 4, 5, 6. We're not counting the 2 electrons in the core shell. We're just counting the valence shell. So it's got 6 valence electrons.
Okay.
Okay, so let's talk about the solubility question on the quiz. What's up?
I was just gonna watch the video.
Oh, yeah. Okay. I'm recording this as well, but we can also do number 19. Okay, so for the solubility question that's been coming up since, what was it? It wasn't the Gibbs lab. Oh, since the solubility lab. Right, so this has been coming up since the solubility lab and the quizzes. And there's a couple different ways that you can logically think about it. In the conversations we had earlier in office hours, I had the realization that I word the question in a way that makes that that I go through the logic in the problem, which is not true for everybody. But let's say, and so I'm just going to call this the solubility question, right? And so the thing that I care about is I always start, I'm going to use silver chloride as an example again. I always start with thinking about it in terms of a solid going to ions. Right? Now, obviously, this only works if we're putting the solid into water, not if we're putting the ions pouring the ions into each other. So in this situation, something that is soluble would be a delta G that is negative. Something that is insoluble would be a delta G is positive, right? Something that's soluble would create products, something that's insoluble would stay as reactants. So spontaneous, non-spontaneous, soluble, insoluble. Then we look at the delta H, and we've got, I should give myself a little bit more space here. Then we look at the delta H. In the delta H, we have 2 different situations. Delta H lat greater than delta H hydration, and delta H lat less than delta H hydration. In this situation, my delta H, I still have to do this even though I've done this so many times. Right, I make the bigger positive because the lattice energy is always positive, but it's greater than the hydration energy, so that's smaller. So this would be my delta H is positive. This one would be my delta H is negative. And I have the same thing down here for my insoluble cases. that delta H lat greater than delta H hydration, delta H lat less than delta H hydration. And so this would be positive in that case and negative in that case. Then to figure out my delta S's, I need the equation delta G equals delta H minus T delta S to do a little bit of logic. So then I got my delta S's. And remember, this is based on observational, so experimentally speaking, I know delta G has to be negative. If delta G has to be negative and delta H is positive, right? This is something we saw, so part of the reason we went straight to observational data for this, right? Back when we were first doing the solubility lab, back in like the end of week 2, beginning of week 3, we said, look, it's actually really hard to get experimental data about delta S. It's pretty easy to get experimental data about delta G because the solid dissolves or the solid doesn't dissolve and we can just watch it happen. It's pretty easy to get experimental information about delta H because the temperature goes down or the temperature goes up. It's exothermic or endothermic, and we can pretty easily see that temperature information. And now we have to figure out logically, with those experimental things that are true, what can we tell about delta S? Well, if delta G is negative and delta H is positive, delta S has to be positive so that we get this minus T delta S. Technically, it also has to be bigger than delta H, but it has to be positive. So we have to have that be positive. So that delta S that goes minus plus plus has to be true. If we're in this other case where the lattice energy is less than the hydration energy, that delta G is negative, the delta H is negative experimentally, right? I don't get to change the sign of delta H. I don't get to change the sign of delta G. Those are experimentally observed. In this situation where delta G is negative and delta H is negative, delta S could be a positive and any value, or delta S could be negative and smaller than delta H. Like T delta S could be smaller than delta H. In either case, since either case is possible, we really can't say anything. Oh, you could just leave the chair up. Someone might come in. See you later. Since either case is possible, positive or negative, either case, I don't know which is more and less likely, I can just say I don't know. I could put some constraints on it. It could be positive in any value, or it could be negative and smaller than delta H, but I just don't know. And that's the kind of logic we go through. We do the same thing with the insoluble cases. Plus plus, unknown, plus minus, minus. And in this last case, it has to be negative, and T delta S has to be bigger than delta H. Again, the problems don't ask us about the has to be bigger condition, but I should probably put that on something, because it's an interesting case. I had this question on the first exam, actually, now that I'm thinking about it. Okay, so that is for the solubility. And this is where, so this is all the information that's in the first sentence. And then that second sentence becomes so important, right? So this would be, and this would be for the delta G, right? How do I write that? I didn't give myself enough space, right? So this is AgCl going to Ag plus Cl minus versus Ag plus Cl minus going to AgCl. We know these two reactions are just opposites of each other, and so all of the signs just flip. This would be, right, and the way we call this is solid into water, and this is mixing ionic solutions or mixing two aqueous solutions, right? We're mixing two solutions, right? That gets the Ag plus Cl minus. All the logic up here is for the precipitate dissolving, if we wanted to do the precipitate forming, we just flip all of our signs. Right? The last thing that seemed to be confusing people, but as I mentioned before I started recording, changing this didn't seem to change people's correctness. These two things, since they're related to the same reaction, right? I could write this as a double arrow. Both of these get called delta G of precipitate. It's just delta G for the precipitate forming or delta G for the precipitate breaking apart. We still call them delta G. I should probably put a standard on there, right? We still call them delta G of precipitates. The same way that when we talk about delta H of lattice, not lattice, sorry. Delta H of fusion for H2O, that can relate to H2O liquid to H2O solid, but it can also relate to H2O solid to H2O liquid. And it's really just recognizing that we're just writing the same thing twice. If I defined two different variables, two different delta H's for this, I'd be just doubling the number of constants in the book without giving any new information. So we just know that the fusion is specifically talking about, like it's just one of these, and then it's just a sign flip for talking about the other one. We do the delta H of fusion for freezing, the delta H of fusion for melting, and it's just one of them is the positive number, one of them is the negative number. Same thing for the delta G of precipitate for the precipitate dissolving or the precipitate forming. And it's just delta G, and we just change the sign of it. Now, again, we talked about a lot of other stuff. I don't need to belabor this. Questions about that? I know we talked about it earlier, so there might not be any questions. If you have questions on the video, come to office hours next time. I'm recording. Okay. I just wanted to get that down. I feel like that was a little more cohesive than the last time I did it as well, so, because I practiced a little. Okay, so we have to pay attention to this. I usually always do this logic first, and then check which type of reaction do I have. If I'm this solid into, then my answer stands. If I'm this mixing two, I just flip all my signs. And that's part of the reason why the questions are formulated in all this information first, and then tells you which system you're doing second. I don't know if me putting the system first would help, but different variations to the question. So let's go ahead, should we talk about the corrosion lab a little bit? Let's talk about the corrosion lab. I'm going to erase this. Okay.
What part of the corrosion lab?
That's a great question. What corrosion lab part do we want to talk about?
It's the post lab one where it's the picture of the gel. And
Ah, yes. That's a weird one. Okay.
Explain this picture?
Explain that picture. Explain that picture.
Well, look in mighty pink so we know that O2 is reacting. And
So we've got two different things, right? We want to explain the differences between the two pictures. Right, so in one of those pictures, I'm just going to try to recreate the picture on the board real quick. In one of those pictures, we've got two dishes. We've got a piece of zinc with a copper wire around it that then goes out of the dish into this other dish that's wrapped around a nail, right? And then we've got the second one, where we've got one dish, where we've got our piece of zinc, we got our nail, and then we got the copper wire wrapped around that, coming out of the dish and then back in, wrapped around that.
for the one on the left, there's no salt bridge.
Yes, that's the important part, right? So when we look at this salt bridge, and we're looking at what's going on, right? This one, we're lacking the salt bridge. Right, so in this situation, we look at everything that's in contact. When we make our voltaic cells, I'm going to switch colors for a sec. When we make our voltaic cells, we have cell 1, we have cell 2, we have electrodes, and we have salt bridge. Right, and the electrodes can be like chunks of things, but we've got some electrodes. Right? And in order for a redox reaction to happen in a measurable way, we need something that allows the electrons to flow, and we need something that allows the ions to flow. We need both of those things to happen. Actually, sorry, that plus is going the wrong direction. Right? So where the electrons are going, cations need to flow to where the electrons are going to keep it charge balanced. Right? And this gets to the importance of a salt bridge in a way that we really kind of neglect unless we understand solution chemistry really well. When we have zinc 2 plus aqueous, we never just have, and the number of times I've drawn it as here's your solution and it's got zinc 2 pluses in it. Can you actually have a solution that's just a bunch of positive ions stacked in together? You'd end up, they would all repel each other. You'd have this like electromotive force. They'd push away from each other. Your solution in and of itself would have some charge in it. So what we do is we have some Cl minuses in there to charge balance it. But we don't care about them because they're spectator ions. Remember, our salt bridge for this lab was sodium chloride. Sodium and chloride were both non-reactive. We don't need to include them in any of the reactions, but they're really important for balancing out the ionic charge of the solution. So we need to have that salt bridge there. In this situation, so that's kind of what's going on, the importance of the salt bridge, the importance of what we call counter ions to counterbalance the ionic charge. We need those counter ions there. So when we look at these two cases, right, we need to have the cation, we need to have the salt bridge and the electrical bridge, the wire, in order to have a complete system. So in this situation, I would have iron, I would have copper, I would have zinc, I would have oxygen, and I would look at all four of those things operating in the same salt-connected system. Whereas over here, I've got zinc, copper, oxygen, and then I've got like no bridge, right? So then I've got this gap, and then I've got iron, copper, oxygen. But since these aren't connected to each other, it's really this thing versus that thing. So I end up with two separate systems there. Yeah.
So then for the first case, like the top petri dish, it would be the iron oxidized and copper reduced? Or is it the flip version?
No. Iron oxidized, and we can tell iron's oxidized because it becomes blue in that picture.
O2 is being reduced.
The oxygen's being reduced. What's the copper doing in this case?
It's the wire, bro. It's
The inert.
yeah. Because with the other one, since there's a salt bridge, the iron can be the inert electrode there. But since there isn't that, now the iron is involved in the reaction on the left one. The two
Yeah.
separate
So we're always going to make the largest possible, the two things that react are going to be the two things that create the largest cell potential. That's going to give us the largest equilibrium constant that's going to produce the most products first. Right, so in this case, zinc and oxygen is going to create the larger cell potential, so those two are going to react first. If we run out of zinc, then the iron will start to react. If we run out of iron, then the copper will start to react.
And if we still have oxygen at that point.
If we still have oxygen at that point.
Is the oxygen coming from the actual like gel, or is it from the surrounding atmosphere?
It kind of both, right? So when we're stirring and mixing the gel, when we're first making it, a small amount of oxygen is getting mixed in there.
Is that what the bubbles are that are escaping?
Kind of. Well, there's oxygen in there. Like water contains some amount of oxygen gas dissolved into it. What do fish breathe?
Oxygen.
They breathe oxygen out of the water. Their gills filter the oxygen out of the water.
So does it just leave, wait, so when fish breathe, do they just like leave hydrogen behind just in the water?
They're not. It's not like H2O getting split to H2 and O2. That's not what's happening. It's O2 aqueous It's oxygen gas dissolved into the water
Oh.
that they're filtering out. So they're able to get it away from all the other water molecules that are
Like,
surrounding
damn,
it.
they're splitting molecules?
No!
Molecules? Like, oh my god.
If they were doing that, we would have had free energy a long time
That
ago.
would be insane.
So yeah. Also, I think the atmosphere would explode.
If we can,
Because we just have hydrogen, if they were just spitting out hydrogen gas into the atmosphere, that'd be problematic. Thermodynamic.
We would
be as
adapt.
well. At some point. Okay, so
I mean,
the last picture that I want to draw real quick to kind of talk about what's going on here is when we've got all of these things going on, right? So we've got our cell, we got our chunk of zinc, it's got the copper wire around it, it's then over here attached to a nail. That's my picture of a nail. Copper wire attached around it. The nail isn't reacting, it's the O2 around it. I'm gonna use purple, but like, you know, it's the O2. Right, it's the oxygen to hydroxide reaction. The salt bridge in these cases, the thing that's kind of weird about the gel we're using is the salt bridge is kind of like everywhere, right? Right, the salt bridge connects everything, like except for this bit of wire that comes out. And so the reaction, the cathode and the anode end up just being this little like fictional tight space around each thing. And then here's the cathode with just giant salt bridge covering everything. And that's how we're able to have the kind of like, the cathode really extends kind of, like we want them to be as far apart as possible, but the cathode kind of extends like across anything that the inner electrode is. Any place where electrons can hop off, we're going to see reduction reaction happening. Does that answer that question? No. Was that your question or is the person who
I
left?
think it was hers, but
Okay, cool. So that's what's going on with that one. Other questions? I'm gonna go ahead and pause/stop the recording. I think that, oh, it's 2 o'clock already.